Hello, good day. In this presentation, I will be talking about the development of integrated sensing technology in the year 2015 till 2021 at Samara National Research University. In general, this work has been conducted at Technical Cybernetic Department under the supervision of Professor Kazansky and Professor Khonina. My name is Ali Bhatt and I am working as a senior scientist at Samara National Research University. So in general, I would be giving you a brief introduction about our research activities towards sensing side. In general, our study was numerical and analytical based, where we have proposed several novel designs of photonic sensors. And here I am going to present four different cases which we have studied. Number one, evanescence field gas absorption sensor, which is based on the optical waveguide, where the propagating wavelength should correspond to the absorption line of the particular gas. As a result, when the device would be surrounded by by this particular gas, it will be absorbed, and the intensity at the output of the waveguide will reduce. As a result, we can detect the presence of the gas. In second case, we have studied the refractive index sensor, which is based on the change in the effective index of the propagating mode. When the light is propagating in the waveguide and comes in contact with the ambient comes in the contact with the change in the ambient refractive index, then the effective index of this propagating mode reduces or changes, and then it can be sensed. In the case of like resonance shift, you can observe. In third case, this is a very hot topic these days, meta surfaces. So different kind of applications has been proposed up till now. However, in our research, we are studying the meta surface absorbers for gas sensing application or reflective sensing application. I will explain you afterwards about this topic more in detail. Then number four is the plasmonic sensors based on MIM waveguide configuration. MIM is the abbreviation of metal insulator metal. So this is also a very hot topic on this on the sensing, because plasmonic sensors are small in size, they are highly sensitive. Moreover, they can overcome the diffraction limit of light. The research carried in the time period of 2015 till 21 lead us to publish more than 80 research articles in highly impact factor journals. In this research, we have proposed the novel design of a double hybrid plasmonic waveguide, which is formed by transforming the standard bridge waveguide. As shown in the figure 1a, the output view of the electric field distribution in the waveguide. This waveguide design has been optimized for 3.392 micron, which is the absorption line of methane gas. So it means that this device can be used for the detection of methane. So how we are enhancing the electric field ratio here? You can see that the middle part of the ridge waveguide is transformed, it's tapered, and as a result, in this part the evanescence field will be high. But we have to transform this evanescence field into the hybrid mode, because hybrid mode is much sensitive than the normal dielectric mode. As a result, we deposited a gold layer on both sides of the waveguide by keeping a small gap between silicon core and the metal layer. So the intensification of the hybrid of this E field in between this between silicon core and the gold layer will be very high. As a result, it can assist us in a very sensitive device for the detection of methane gas. In figure B to D, we can observe the electric field distribution at the input, in the middle part, and at the output. So we are trying to keep the dielectric mode at the input and output, because it is easier to launch the light at the input and also to receive it if they are in the dielectric standard dielectric waveguide configuration. However, in the middle part, we have a hybrid mode on both sides of the core, which is the main, which plays a main role in the enhancement of electric field, and will be more absorbed, and the more light will be absorbed by the gases. by the methane gas. In figure 2, we have shown the experimental setup where you can see that the optical waveguide is surrounded by a chamber, and in this chamber we are launching the methane gas from the inlet, and it's taken out from the outlet. The light is coupled from the input section of the waveguide and it is received from the output section. So here we have to check the decay in the in the intensity of the propagating light, and then after we can take a ratio between the output over input, which gives us the efficiency or device performance. Up to our research or knowledge, we have demonstrated that the performance or the sensitivity of this device is higher than the sensitivity of the devices based on conventional ridge or rib waveguides. More detailed information on this topic can be found in our research article published in IEEE Sensor Journal in the year 2020. In our next research, we have studied the 4 different waveguide structures for refractive index sensing application. In figure 1a, you can see the slot waveguide, which is in its standard configuration, and this structure is highly attractive for sensing applications because of its high field confinement in the slot region, and which provides the additional or enhanced interaction between this E field and the ambient medium. In figure B, you can see the double slot waveguide structure. This can also provide an additional interaction of electric field, which is confined in 2 slots with the ambient medium. In figure C and D, to enhance the interaction, there is another kind of waveguide which is known as sub-wavelength grating waveguides, and we have used this in slot waveguide structure. So when we combine these 2 structures together, it results in the sub-wavelength grating slot waveguide. In figure C, you can see the single slot, and in figure D, we have utilized double slot sub-wavelength grating double slot waveguide. To understand their sensing performance, we have designed sub-wavelength we have designed the racetrack ring resonator based on all these 4 structures and compared their performances. Out of all these, the best performance of 1000 nanometer per refractive index unit was obtained for double slot for a sub-wavelength grating double slot waveguide ring resonator. And this value is the highest up till now into the literature which we can find, because the sensitivity of conventional ridge waveguide ring resonator structures is up to 200 till 300 maximum. But because of this unique waveguide architecture, we have an additional electric field interaction between the analytes and the light propagating into the ring resonator. This work was published in Sensor Journal in 2020, and the detailed information about this work can be found there. Our next research was related to the metamaterials and metasurfaces. Basically, metamaterials and metasurfaces have opened the wide avenue for the realization of novel electromagnetic properties and functionalities through tailoring sub-wavelength structures and integrating functional materials. Over the past few years, metasurfaces have been employed for the design and fabrication of optical elements and systems with abilities that surpass the performance of conventional diffractive optic elements. In this work, we have proposed an attractive design of a carbon dioxide gas sensor based on polyhexamethylene bigonide polymer. Afterward, we will call it PHMB for simplicity, deposited on a silicon nanocylinder metasurface. The device design is shown in figure 1, where we can see that a gold layer is deposited on a quartz substrate. Afterwards, on gold, we must deposit an array of silicon nanocylinder. So this structure now is a metasurface. On that, we have to deposit a carbon dioxide sensitive PHMB layer. When the carbon dioxide is around, this layer can absorb the carbon dioxide. As a result, the refractive index of this layer changes, which in turn shift the resonance wavelength of the absorbed light. Perfect absorbers have been a hot topic in metamaterials for a lot of years. The first realization of a perfect absorber was published over 30 years ago, and ongoing research is developing, improving, and finding new and innovative ways to demonstrate and fabricate perfect absorbers. Carbon dioxide is a colorless, odorless, and non-flammable greenhouse gas typically generated by the combustion of carbonaceous materials or by the metabolism of animals. The current carbon dioxide gas concentration and its growth rate is leading to a global warming and unsustainable environmental challenges. For that reason, high sensitivity carbon dioxide gas sensors have been widely researched to track patterns in the concentration of greenhouse gases. As the concentration of carbon dioxide in the ambient medium increases, the refractive index of the functionalization layers changes. PHMB has basic amide bearing functional group and is a member of guanidine polymer family. It's an ideal contender for a functionalization polymer layer that is equally sensitive and selective to low concentrations of carbon dioxide at room temperature and atmospheric pressure. The resonance wavelength blue shift of gas sensors based on the functional material of PHMB is linearly interrelated to the carbon dioxide concentration. The reflection spectrum of the proposed sensor with respect to the gas concentration is shown in figure 2. So the proposed gas sensor is capable of detecting carbon dioxide gas within the concentration range of 0 to 524 ppm with a maximum sensitivity of 17.3 pm by ppm. The proposed sensor configuration can be utilized for the detection of other toxic gases by utilizing suitable functional host materials. The detailed information on this topic can be found in our research paper, which was published in Sensor Journal in 2021. The last topic of our research discussed in this presentation is about plasmonic sensors. The word plasmonics defines photonics related to the surface plasmon and has stimulated substantial interest since 1990s. The antiquity of the surface plasmon study goes back as early as the 1970s to the finding of surface plasmon resonance on a thin film and light dispersion from nanoscale metallic specks. Surface plasmons are of two kinds, the localized type, which is known as localized surface plasmon polytron LSPP, and the propagating type which is surface plasmon polytron. So in our research we have basically focused on the propagating type, which is SPP, electromagnetic waves. Plasmonic sensors are commonly used in food safety, colorimetric sensor, alcohol sensing, fuel adulteration, early disease detection, biosensing, medical diagnostic, telemedicine, bioimaging, underwater temperature sensor, and so on. Some of the most relevant application of SPR sensors are shown in the figure 1, which you can see on the screen. It has been used in optoelectronic devices such as SPR imaging, optical filters, and modulators due to the continuous development in the SPR technology. An SPP-based research paper was recently published in Japan for the rapid detection of COVID-19 when the viruses are caught. Antibiotic-coated gold nanoparticle undergo resonance peak shift, exhibiting a distinctive color transmission. In pregnancy testing, similar procedures are commonly applied. Plasmonic sensors based on metal insulator metal waveguides are highly attractive, and they have been researched throughout the world. Researchers are trying to increase the device performance by proposing unique cavity designs. On the screen, you can see the different kinds of plasmonic sensors based on metal insulator metal waveguides are shown. Here, there are different kinds of cavities such as bow tie with cavity filled with dots, nanodots, or some ring resonator, some square cavity, or Bragg grating. So these efforts are leading us toward the high device performance. In recent years, we have worked on plasmonic sensors based on MIM waveguides for refractive index or gas sensing applications. Here I am sharing with you our recent research paper on plasmonic waveguide for gas sensing application, which was published in Optics Express. The square cavity, which is coupled to the MIM bus waveguide, is filled with a PHMB functional polymer. And as we have discussed in our previous section, that this PHMB is sensitive to carbon dioxide gas. And when this sensor comes into the contact with carbon dioxide, the resonance wavelength performs a blue shift because of the change in the refractive index of the material. In figure 1, we have shown the schematic representation of the plasmonic sensor where the functional polymer is filled in the cavity, and in the lower part we have shown the H field, magnetic field distribution at off resonance and on resonance wavelength. It means that when there is no resonance condition, the light can transmit from the input to the output. However, at resonance condition, the light will be completely coupled to the square cavity, and then there will be no transmission at the output. The sensors based on SPP waves are highly sensitive due to the strong interaction of the electromagnetic wave with the matter. By utilizing PHMB polymer in the MIM waveguide, plasmonic sensor provides a platform that offers the highest sensitivity of 135 picometer per ppm, which cannot be obtained via optical sensors based on silicon photonics. The sensitivity reported in this work is around 7 times higher than reported in the previous works. Therefore, we believe that the results presented in this paper are exceedingly beneficial for the realization of the sensors for the detection of toxic gases by employing different functional materials. Our ongoing research is focused on photonic crystals. The engineering of electromagnetic modes at optical frequencies in artificial dielectric structures with periodic and random variation of the refractive index, enabling the control of radiative properties of the materials and photon localization, was first proposed independently by Yablonovich and John in 1987. It is possible to control the flow of light in the periodic dielectric structures known as photonic crystals. Up till now, we have successfully demonstrated the one-dimensional and two-dimensional photonic crystals for light steering application and polarization splitting. Our future goal is to explore its capabilities for sensing application and logic gates. In the end, I would like to bring your attention towards our review papers, that we are not only focused towards original research papers, we are also writing some interesting review articles based on the area of our expertise. And these papers have been written with universities within Russia and out of Russia in collaboration. So we are quite open for collaboration on some interesting topic to write some review articles. In conclusion, we have successfully analyzed the photonic devices with the help of finite element method by using COMSOL multiphysics software. At the moment, we have achieved the following goals. Number one, gas sensors based on evanescence field gas absorption phenomena. And these devices were designed on conventional waveguides and unconventional waveguides. For example, RIB, RIDGE, slot waveguide, hybrid plasmonic waveguide, and SWG waveguide. Refractive index sensors based on novel architectures were studied in SOI platform, plasmonic platform, and metasurface. And recently we are working on the photonic crystal structures, and we have successfully demonstrated beam steering and polarization splitter or polarization maintaining devices. And we are extending our research to explore more potential applications based on these novel structures. Thank you for your attention. Don't hesitate to contact me if you have any question regarding the research carried out in our group. And if you have any novel idea which you would like to implement together with us in collaborative work, my email ID is given in the slide. Thank you.